Okay, good afternoon, everybody. My name is Christos Kozirakis. I'm the faculty involved with this work, and I'm going to introduce Colby and kind of give you a little bit of a background for this work. So about 2.5 years ago, one of the students in my master's level architecture class brought me the MapReduce paper, and he said, it's a great paper, we should probably talk about it in the class. And I read it and I thought that, those lucky people at Google, they have the easiest problem on the face of Earth. It's read-only, good for them. Why should I care? And then we spent quite a lot of time talking about maybe some other applications map into this model, and eventually I started turning around. So now MapReduce ends up being part of what we do in this class, the 282 class. And then eventually in another class, 382, I managed to find 3 bright students to give it a try to see if you can take exactly the same model and use it to program multi-core machines. So Colby, Raman, and Arun are 3 master's level students at Stanford who did exactly that. Within a quarter, they did a shared memory runtime and implementation of MapReduce, which is not necessarily the most robust thing on the face of Earth. It was still what they were able to do in 3 months, but it showed some very promising results. So Colby will give the talk, who is finishing with his master's degree in a few months, and he's supposed to start here in April, so feel free to abuse him.
I don't know about the abuse. So I'm going to be presenting an evaluation of MapReduce for multi-core and multiprocessor systems. And I worked with Ramanan and Arun on this with some help from Gary and Professor Kozarakis. So MapReduce was developed by Google as a general purpose parallel programming model. It is designed to be used on very large data sets and maps parallel tasks to thousands of computers in a cluster. It's nice because it takes a functional representation of an algorithm and allows for the automatic abstraction of data parallel tasks. It's proven to be very successful within Google since it's easy to use and maps very well to web indexing applications, distributed grep and sort, document clustering, among other applications. Its ease of use comes from the fact that the parallelization, synchronization, and communication issues are abstracted away from the programmer. In addition, it provides some level of fault tolerance through task monitoring and task replication. So let's see how an example application would map to this model. Here's the original word count example from the original MapReduce paper. It counts the total frequency of occurrence of all the words in a document. It's broken into 2 functions, the map function and the reduce function. So for the map function, it's applied to each element of the input. In this case, we take in a document and emit a word and an occurrence of 1 for each word in the document. And this is our key value pair that's stored in the intermediate queues. For the reduce function, it's applied to all pairs from the intermediate queues with the same value. In this case, we take in a word and a set of occurrences. We sum the set of occurrences to get the total frequency of occurrence and emit the word and the total frequency of occurrence as the final key value pair. The output is a set of lists sorted by keys. So even though we have this simple functional representation of map and reduce, this can be run in parallel across different sections of the input and intermediate pairs. Given this function, Google used this to run it on thousands of computers. But we want to explore if this can be applied to CMPs. As we all know, all the major processor vendors are turning to CMPs, and the critical question is, how do we simplify the programming of these devices? Given that MapReduce abstracts away the parallelization, synchronization, and communication issues from the programmer, it makes it a good candidate model. So, to show that MapReduce is applicable to multi-core program, we need to answer a few questions. What is the performance? Is the performance scalable and portable? Does it help with locality and fault management? And how does it compare to other parallel programming approaches? To explore these questions, we developed Phoenix, a shared memory implementation of MapReduce. It takes parallel tasks and maps them to shared memory threads instead of computers. It runs on a single shared memory machine, and the current version works with C and C++ and uses pthreads as a threading library. However, this should be easy to port to other programming languages and threading environments. As with MapReduce, our model can be broken into 2 parts, the API and the runtime. So let's take a look at the API. This is a C-based API, and here's an overview of it. It's divided into two parts, the system-defined functions and the user-defined functions. The system-defined functions are the ones provided for you. It includes a call to the Phoenix scheduler, which initializes and controls the environment, emit intermediate and emit, which are called from MapReduce, to store key value pairs into the Phoenix managed queues. The user-defined functions are arguments to the Phoenix scheduler. These must be provided by the programmer. It includes map, reduce, and the key comparison function. The key comparison function is used when emit intermediate and emit is called to sort the keys. In addition, the programmer can specify the splitter function, which splits up the input data for the map task to process. This is optional since, by default, we have an array splitter function. As you can see, this is a simple and narrow API where you only need to specify a few functions. There are some more arguments that the programmer can specify that aren't discussed here, but are discussed in some more detail in the paper. So, a call to the Phoenix scheduler starts the Phoenix runtime. This is what orchestrates the program execution across multiple threads. This includes starting and stopping of worker threads, assigning map and reduce tasks to workers, and handling buffer integration. The key features of our runtime, which help improve the performance, include dynamic scheduling of tasks for load balancing, trying to reduce communication by using pointer exchange instead of data copying whenever possible, optimizing for locality by breaking up the data and algorithm into smaller chunks, and providing some support for fault recovery. As with MapReduce, the details of parallel execution are hidden from the programmer, including low-level threading, communication, and scheduling. That way, the programmer can focus on the functional aspects of their algorithm. So here's a pictorial overview of the Phoenix runtime. It starts with a call to the Phoenix scheduler, which passes the input data to the splitter. The splitter divides up this input data into chunks for the map task to process. The map task processes this data and emit it into intermediate queues. After all the map tasks finish, the reduce stage starts. The reduce stage processes the data from the intermediate queues and emits the resulting key value pairs into the reduce queues. The merge stage combines all the reduce queues into a single output queue. In the next few slides, I'm going to discuss the map, reduce, and merge stage in some more detail. And I'll provide some insight into how Phoenix manages the execution. Also, I'll give some trade-offs for the programmer to keep in mind when using the model. So the splitter function divides the input data into chunks for the map task to process. It does pointer manipulation, and it has to deal with some trade-offs when it's choosing a chunk size. If the chunk size is too small, there could be increased overhead from starting and stopping of map tasks. If the chunk size is too large, you could have some locality problems or possibly some work imbalance issues. Phoenix attempted to explore these trade-offs by choosing a chunk size determined by the cache size to optimize for locality. Again, the program can provide a splitter function. However, by default, we have an array splitter function provided for you. So let's see how this data is processed. The map stage is composed of workers, where each worker runs on a separate thread. Each worker runs multiple map tasks, and typically an application has hundreds of map tasks dynamically scheduled across all the workers. So, as the map tasks process the chunks of data from the splitter, they call emit and store the intermediate key value pairs into the intermediate queues. The partition function makes sure all the keys of the same value get assigned to the same queue. Since we need to combine all these keys of the same value, partitioning can introduce significant overhead. After all the map tasks complete, the reduce stage starts. The reduce stage, again, is composed of worker threads where multiple reduce tasks run on each worker. The reduce task will process the data from the intermediate queues. The partition function, if the partition function unevenly distributes the keys across the queues, there could be some work imbalance, which is why we use dynamic scheduling to help alleviate this problem when we run reduce tasks. So as the reduce tasks process this data, they emit it to the final key value pairs to the reduce queues. Now the partition function, by default, is just a key hashing function. However, the program can provide a custom partition function if they know more about the distribution of the keys. So after all the reduce tasks finish, the merge stage starts. In the original MapReduce model, it simply ended at the reduce stage, and the final output was this set of reduce queues. We added the merge stage, which combines all the reduce queues into a single sorted output queue. This may be unnecessary for some applications, but the merge time tends to be small when compared to the map and reduce stage times. In addition, it's convenient for many shared memory applications to have this. How it works is we do a binary merging of reduce queues until there is a single sorted output queue. And that's the overall execution of our runtime. So I've told you how we can parallelize all these applications with all the workers and tasks running on them. However, some things can take away from the speed up. Some of these things are significant, while others are either infrequent or easy to fix. I've already said how partitioning can be a major overhead, since we need to combine all the keys of the same value together. In addition, repeated calls to emit and emit intermediate can introduce overhead, since we need to do some data copying. Some problems are related to how the programmer uses the API rather than how the runtime manages it. This includes key management, since some applications do not naturally associate keys with data. What this means is, in the original implementation of the algorithm, these keys did not exist, so the programmer had to introduce them, which made it more difficult on the programmer, and it was pure overhead for the runtime. Another issue is, some algorithms are iterative and require multiple invocations of the MapReduce scheduler, which is an expensive operation. Some of the more insignificant issues include the final merging and sorting of reduce queues into a single output queue. But when compared to the map and reduce stage time, this tends to be small. In addition, buffer management tends to be a smaller issue, since we aggressively reuse pre-allocated buffers. We deal with reduce imbalance by dynamically scheduling reduce tasks, so this tends not to be as much of an issue. And one can imagine the input splitting function being a serialization point. However, most map tasks contain enough work, so this doesn't actually happen. I just wanted to bring up a few high-level issues on this slide, since they're going to affect the performance later. And there are good things to keep in mind when using this model. But before we get to the performance results, let's talk about the fault tolerance model we used. We focused on transient and permanent errors in the worker, and our error detection scheme was based on worker timeouts. So if a task tended to be running a little bit longer than the other tasks, we assume it had an error and start the error recovery process. It included restarting the task, and if that failed after multiple times, we assume the worker had a permanent error, and we reassign that task to a different worker. The scheduler handles input and output buffer integration for you when these errors occur. In the future, we'd like to add fault tolerance for the scheduler and do some error detection and isolation through worker sandboxing. So to evaluate Phoenix, we used an SMP system and a CMP system. The CMP system had 8 CPUs on a single die and hardware support for 4 threads per CPU. The SMP system had 24 CPUs. We found the SMP results to be very similar to the CMP results, which means we got portable performance. What this means is, you can write one version of the application and it works well on both machines. I'm not going to discuss the SMP results today, but they are discussed in the paper. We wrote 8 applications from 3 different domains, the enterprise, scientific, and consumer domains. In addition, for each application, we had 3 code versions, the sequential, MapReduce, and pthreads version, each of which were optimized independently. Today, I'll talk about how our model performed and scaled, and how the model performed versus pthreads. In the paper, we discussed dependency to dataset size, dependency to input task granularity, and how soft and hard fault injections affected our model. So here are the 8 applications we wrote. I'm not going to say how we actually wrote them in the MapReduce model here, but it's discussed in the paper. I just want to bring up a few high-level issues associated with these programs here. These programs on the top, like reverse index, matched well to the MapReduce model and seemed to perform well and were easier to write. These applications down at the bottom didn't necessarily perform poorly, but they had other issues associated with them. For instance, K-means is an iterative algorithm and required multiple invocations of the MapReduce scheduler, which is an expensive operation. In addition, PCA and histogram required the programmer to introduce keys that weren't in the original algorithm, which made it more difficult on the programmer and introduced some overhead in the runtime. But just because you need to introduce keys into the model doesn't mean your program has to perform poorly. In the case of matrix multiply, we introduced a coarse grain coordinate as a key. But we associated this with a large enough chunk of data such that the overhead was amortized in the runtime. So here's a graph of the CMP speedup of the Phoenix version of the application versus the sequential version of the application as we scale the number of cores. Higher is better. We ran it on 2, 4, and 8 cores with 4 worker threads per core since we had hardware support for it. So as you can see, we get pretty good speedups, with the worst speedup being about a 8x speedup on 8 cores for k-means. What this shows is we get pretty good performance, and it scales. For some applications, we get a superlinear speedup as we increase the number of cores. This is because we're breaking up the data into smaller chunks and the algorithm into smaller chunks, so we get great caching effects, and there's reduced work per task. For other applications, you see a flattening as we increase the number of cores. This is because we're running 32 worker threads, and all in parallel with workers, and some bandwidth saturation takes place when this happens. In addition, load imbalance can take place at high core counts. So Phoenix seems to perform well and scales, but how does it compare to other parallel programming approaches? Pthreads is a low-level API that is much more flexible than Phoenix since it doesn't impose a structure on the programmer. In Pthreads, you could do exactly what Phoenix does, or you could do some other parallelization technique. What this means is the performance for Pthreads should be at least as good as Phoenix. In this graph, we have the Phoenix version of the application versus the Pthreads version of the application as scaled against the sequential version of the application on 8 cores. Again, higher is better. So for some applications, we see that Phoenix performs comparably to Pthreads. And that's because these applications match the MapReduce model well. You notice that Phoenix actually performs a little better than Pthreads in some cases. And that's because we dynamically scheduled tasks in Phoenix, whereas we statically scheduled them in Pthreads. An interesting anecdote is when we were writing some of the code for Pthreads, we actually looked at the behavior of Phoenix to tune the code for our Pthreads. For other applications, we see that Pthreads actually performs better than Phoenix. That's because these applications do not match the MapReduce model as well, either because we had to introduce keys or it was an iterative algorithm. So we seem to get pretty comparable performance with Pthreads, and we're pretty pleased with that. Even though we may not get the best performance all the time, this tool really does simplify parallel programming, and it is a useful tool. In conclusion,
what's going on in the reverse index case?
So are you talking about why the numbers are so large?
Why they're so large and why Phoenix is so much faster than Pthreads?
Well, maybe I'll wrap up the conclusion and come back and answer that right away. So it'll take a few minutes. So Phoenix is a shared memory implementation of MapReduce, where we take parallel tasks and map them to shared memory threads instead of a computer. We run it on a single shared memory machine, and we provide some key runtime features that help improve the performance, such as dynamic scheduling, locality management, and fault recovery, among other things. I've shown we get scalable and portable performance, and it compares fairly well to Pthreads. In this research project, in the short amount of time we had to do it, I think we've shown that it works, and it's an interesting thing to do. As with many research projects, I'd like to improve the queue structures, automatically detect some system configuration, add better fault detection, and experiment with more systems and applications. So this is where we'll make a copy of the source code available, and we'd appreciate any comments you may have on that. But let me get back to that question you asked. So the question was, why is this performance on reverse index ridiculously high? And the answer is the algorithm we chose for reverse index in the sequential case doesn't scale well as you increase the size. It's an n-squared algorithm. So that's why you see the much larger increases. So when you break up the algorithm into smaller chunks, you get much better speedups. Does that answer your question?
Why is the speed up for Phoenix so much higher than P-threads?
So why is the speedup for Phoenix so much better than P-threads? That's because when we do the Phoenix version of the application, again, it's not just that we statically schedule well, it's mainly because we statically schedule tasks in P-threads. So this shows up much larger in this case because the data set is very large. It's in the gigabytes range. So, and these documents that we're running it across, you can't tell how much actual links you're going to have in a document just based on the size of a document. So even though you break it up into equal chunks, these tasks have different amount of work that don't get balanced as it does in the Phoenix case.
What would the speed up be if you use the same algorithm for a serial and parallel case?
What would the speed up be if we use the same algorithm for the serial and
Parallel case for reverse index?
if we broke it up into smaller chunks in the serial case? And
You're in the same code, but not. I'm assuming you don't actually need threading.
Right. I'm not sure what the speed up would be exactly, but
So it is the same algorithm, it's just that it's not the best algorithm. It's an n-squared algorithm, so if the n is lower, because every task is doing a much smaller n than what the sequential program does. Well, then you get square effects, right?
You can say it's the same algorithm, but it really isn't. You're not running the same stuff.
No. So your question should be, I guess, what if you use the not n-squared algorithm? What's the speed of the data? So it is the same algorithm, it's just that this one favors a parallel implementation much more than favors sequential.
okay. Are there any other?
Comparison is not valid then, because you are giving favor to a parallel algorithm that has lower sum of squares.
So you can basically take these results and cast them whichever way you want. And one thing that you could say is, oh, you didn't do dynamic scheduling in the P-threads case. That seems unfair. And when it comes to ultimate performance, it seems unfair. And I think that, if you give me an infinite amount of time and the lowest level API than P-threads, I will beat anything you can do with anything higher level like our MapReduce implementation. I think the question is within some amount of time and some reasonable programming knowledge, what can you do? So in this case, we wrote the same program. In one case, the runtime did dynamic scheduling for you. The other case, you had to go and implement it. And you will not get all the parallel programmers out there to put enough time basically to figure out which is the best algorithm for this specific machine, or as a scale the machine how to adjust the algorithm. And one of the points here is it's nice to have a model where you write it once and it does reasonably well, maybe not optimized all the time or not. And I think that if you just focus on what is the peak performance and what can you do with infinite amount of time, it's not necessarily what we're trying to get here. The question is what can reasonable people do within a reasonable amount of time.
Yeah. Another topic, how large are these data sets, and what is the thing that's gating your performance on these various problems? Is it memory bandwidth? Is it pure compute bound, memory bound, I/O bound?
It really depends on the application. First off, the question was, what are the data set sizes we're using, and how are we gauging performance?
No, what's limiting it?
Oh, what's limiting our performance? Okay.
Memory bandwidth, things like that.
Well, as far as data set size goes, it varies in sizes. It's mainly based on runtime. So for the reverse index, we could do gigabytes of data in a very fast amount of time, whereas for these other algorithms, because you only have a linear pass really through one of those, Whereas if you're doing like a matrix multiply, you use the same data a lot more and keep on passing it around, so we use smaller data sets for that. In the paper, we discussed the actual sizes we used. I don't have that figure with me right now. Now for what's actually limiting performance, it really depends on the application. And I mean, it varies because, you know, you got k-means, you know, which is an iterative algorithm. And then you have other problems where you need to introduce keys. And for some things, I think that flattening effect, as you saw in the higher, that flattening effect, that's where you, in those applications, you tend to get that I/O congestion. So there's really no one answer to what slows down a program. It's really on a case-by-case basis and how it actually breaks up the data and how it uses the data.
So I think we actually go to see pretty much everything. In the sense that sometimes you just saturate the machine.
Mm-hmm.
Yeah, so saturate the interconnect.
Okay, suppose I have some.
None of them is I/O bar. These things all fit in memory because that's what we focus on.
Suppose I have some amount of money to throw at the problem. Would I want to increase the cache size? Would I want to add more cores? Would I want to do what? To make it go faster.
We don't have the figure there, but the cache size will not a big effect because once you chunk it, locality works pretty well. In some cases, the interconnect, you know, the off-chip bandwidth becomes an issue because they all try to stream data in and stream the output out, and none of the problems that we run was big enough to exercise the I/O system, so we kept not doing that.
Yes?
Okay, I have two questions. One is, did you compare Phoenix with the original MapReduce models? So you have 4 CPUs, 4 cores in your machine. Compare that with like MapReduce on 4 machines, for example.
Oh, I see what you're saying. So did we compare our implementation versus the original MapReduce implementation running on separate machines? And no, we didn't do that. Sorry.
The other question was, how does the program model or the ease of programming, ease of use give you like more high-level feature, like for example, futures in Java or ML, those functional or object-oriented languages? How does it compare to them in terms of ease of programming or use?
So how does our programming model compare to other higher-level parallel programming approaches? Well, there are functional models, which makes it easier on the programmer in both cases. And as far as performance, we don't have any statistics on that. But for ease of programming, you know, I think, I'm not really sure, but there are similar approaches. It's just our MapReduce implements some structure on the programmer with a map and reduce stage, whereas in those other models, you have a little bit more flexibility.
I think a conclusion here was something like, you know, if it kind of fits the model that you guys developed, this is a very nice high-level programming environment. That's something amazingly simple. Then the runtime handles the locality, the chunking, the fault tolerance, everything. If it doesn't fit the model, then that's where the weird stuff happens. That's where the comparison with other stuff gets interesting. So, for example, you know, with some programs, you know, remember, I think linear regression was one of the PCA. That didn't have keys. So you have to come up with keys. And forget whether it was fast or not when it ran. That was an exercise, okay, which wasn't natural because you didn't have them in the algorithm. So in that case, maybe using OpenMP or your favorite Java thread package and so on, it would be a more natural experience for the program. So I think that, you know, if you look at many things that are happening in many places, including Stanford, nobody's trying to say, here's one programming model, whether it is features, OpenMP, you know, transactional memory that we're heavily involved with, you know, this version of MapReduce and so on, it's good for everything. It's more like, well, maybe we can have something which is good for a class of algorithms. You look up based on this kind of algorithms, which is the best environment. I code it very quickly and move on with my life. Some of the, you know, the nice thing about this one is that if you express this way, everything is taken care of. While with features, for example, you know, you still have to worry about some issues like how do you join things and so on. You better get right. If you don't, you have an incorrect part of the program.
Yes?
Could you describe the partition step in a little more detail?
Sure. let me bring up the overall picture. So this partition step you see at the end of the map stage, this is what makes sure all these keys get assigned to the same queues. And I think what you're trying to get at is how do we reduce contention when you're doing something like this, right?
That's part of what I'm trying to get at. The other question is maybe on the other side of, in that other gray
where you see the all-to-all.
How do you arrange so that all values associated with the same key are presented contiguously to the reducer?
Right. So how this works is for the partition function, we actually keep, for each worker thread, a set of queues for each reduce task that's separate for each thread. So there's no communication when you insert into these queues. You only need communication when you combine, which happens when you start your reduce tasks. And since that reduce task is only going to be using that values, there's no contention for those reduce queues that it needs. So you can just combine them. It just goes through, compares the front of them, and combines all the keys of the same value, and starts a reduce task.
But we didn't necessarily collect the statistics, but I would expect that this is where you see all the
Yeah.
hearers traffic in the CMP
This is
shooting through the roof and saturating buses.
Yeah, since we're grabbing data from every thread, there is a lot of communication here, and it's definitely where we should look into improving either the queue structure or the partition, how we actually partition here. Yes.
Do you use an n-way merge before you feed data to reducer?
Yeah.
So why do you use n-way merge here and not in the merge stage?
Well, you mean?
In the merge stage, you merge on a binary tree.
Right, because we do it that way because then you can run them in parallel on different sections, and there's no guarantee that the keys in the lower, if it's just a basic hash function and we're sorting it as we're going down, we want to do it all in parallel because you can get more bandwidth that way. If you did it as an n-way merge, you'd have to do it all on one processor there, and we yeah.
The root of the tree has to be
Right, that's a linear pass through all the data at the last node.
I think the honest answer is that the last stage didn't really matter. So.
But I mean, the merge time was very minuscule. I mean, compared to these map and reduce stage times. So we didn't optimize the merge stage maybe as much, and there's more we can do to optimize that in the future.
Now, suppose that your mapper and reducer are trivial.
Mm-hmm.
Then would merging appear as an over, a significant over?
Yeah, it could be more significant in that case, but it depends what exactly the application is. You know, if you're just doing something like running through all the data in your map task, just emitting it, and then reduce task is just emitting it, and then your merge stage is just sorting it, it could be more significant in that case, yes.
Most of the sorting goes on the partition stage.
Yeah. So assuming you have a good partition function, this merge stage should just be combining near queues that are already sorted.
Actually, if you have a completely trivial MapReduce, even the splitter, the way to implement it can become important.
Yeah.
So you do sequential splitting, one at a time, and if everybody else says, nothing.
Mm-hmm.
But we haven't run to any application that had nothing to do with both MapReduce.
I see. So one potential area to look at is how to make concurrent splitting.
Yeah. Any other questions?
Maybe one thing you should do is to say where the paper is, because I forgot to introduce it and you referenced it 20 times. So.
Okay. There's one more question.
Yeah. Did you try this on any NUMA architectures?
No, we didn't. The model, we haven't tried it on that, but.
We switched off our last.
The question was, did we try it on any NUMA architectures, by the way?
You mentioned that
Yes.
The reduce work?
In reduce work, yes.
And could you elaborate on this?
Sure. So for these worker threads, like I said, we had 32 in the case of this one machine, but we usually have one per processor. And the number of reduced tasks exceeds that. So you can run multiple reduced tasks on a given worker if it completes. So as reduced tasks complete, you start the next one. That's how we dynamically schedule them. And the reduced task includes the merging of all the keys and then running it for reduced task for each key.
How many more reduced tasks do you have?
I mean, it depends on the data set size, really, because we wanted to break it up, these reduced tasks, to work on smaller chunks of data.
If you look at, there is an overhead as you modify the,
Oh, yeah.
the number.
Yeah.
As you keep on increasing
It can be a,
those tasks, the overhead grows. Did you look at an optimum value for a given, say, word count or some other application on your specific application?
well, I would say there is an optimum range, and we definitely played around with these values to get the best performance we could, and that took some time to figure out what that would be. So it varied from application to application, since the distribution of keys is not necessarily the same for each application, making the number of reduced tasks that's optimal different. But generally, I really don't have the answer for that question, but we can do more research into what exactly would be a good methodology to figure out what the optimum number of reduced tasks is.
I think typically for most applications we had several hundred reduced tasks, and that seemed to work well. One of the problems that we actually ran into is as we increase the number of reduced tasks, we increase the runtime of the merge stage, because now the merge stage has to reduce more queues.
Mm-hmm.
So we did run into those problems, but we haven't explored it probably as fully as we would have liked to. But generally in the order of several hundred reduced tasks when we had like 32 or 34.
In addition, as you increase the number of reduced tasks, as you had with splitting, there can be some contention as you're starting map tasks. There can also be contention for figuring out what the next reduced task is to schedule if these reduced tasks have nothing to do. If there's no keys in the queue, then you're going to be waiting on this lock to get the next chunk of data if there's no data for you.
So in this situation, I believe that n-way merge may be better, because here you're touching a data, bringing it from the main memory log and times, while with n-way merge you could keep the heap inside cache, and then there will be just cache much faster operation of picking up the minimum and then feeding a memory key value get from the main memory to cache or pointer, and then it will get to so the light will be from main memory to cache. It may stay in cache, move around cache for a while, and then go to main memory. So the number of main memory accesses will be smaller. So this is why I was curious why you use this binary tree merging. Since cache might help.
Mm-hmm. So, are there any other questions? Yes.
Sort of a generic one. For those applications that the model fit well,
Mm-hmm.
How much tuning did you have to do to get a reasonable speed up over the sequential case?
Oh, to get a speed up over the sequential case? Once we played around with the scheduler to figure out what the optimal chunk size would be for these applications, it didn't take that much tuning. Just that was mainly picking a chunk size that fit into the cache, and that was pretty quick.
When you say tuning the scheduler, was that tuning the scheduler to the application?
Yes, you can tune it to the application. You can give it some idea. Well, by default, the scheduler will pick data a size based on the cache size. However, the user can provide some hints based on how much work you actually do on this data. If you
So let me rephrase the question then. How good was the default?
Default's pretty good, and we didn't change it for a lot of applications after we played around with it, and it turned out to be pretty good.
So I guess I can answer because I was getting the results in stages, right, as opposed to seeing it an hour per hour. And the initial results were not stellar, but there was always significant splitting.
Mm-hmm.
Okay, and then they basically had to play with the splitter. It's not really changing the schedule, providing the schedule for better splitter. So there was a little bit of going back and forth because the apps and the whole runtime was code with that essentially. Opposed to what was happening in the production environment where you have a runtime and it works and you develop applications and just minor tunings in the runtime.
Yeah, so after we got through the first batch of applications, the other applications after that, we didn't really have to play around with anything.
I think the interesting thing is try more applications, see if we run these cases where map is trivial and merge ends up being a problem and so on. So these are 7, 8 applications that we don't really know what they are. So there's still much more experimentation before we fully understand what. It's a typical problem.
Any other questions?
Do you have any lessons which would be applicable to some of the others of the 13 dwarfs that Henderson has?
So, what was the question again?
Do you have any lessons which would be applicable to some of the other of the 13 dwarfs that Henderson presented?
You remember the list? I remember it by heart.
No, I'm
So I think it's worthwhile somebody going down the list and see if they can be MapReduce one way or another. I don't remember the list whatever, so I went through a couple of revisions of that technical report. So, but if you think about most of them, maybe FSM stuff is the exception. I don't remember the whole list. Are fairly data parallel. I cannot remember whether they actually have keys or they won't matter much if you use keys or something like that. But let's face it, if you think about scalable parallelism, if you're thinking about 1,000 cores on a chip, it has to be data parallel. Because there's no way that anything else will be easy to write. It cannot be 1,000 different tasks. Who will write the program with 1,000 different tasks? So after a certain point, it's all data parallel. Whether it's going to be functional style data level parallelism or more SPMD, we do OpenMP stuff or something like that. I'd like to go back to the list and see if it works. But it's never going to be data parallel, not much. I think you're right.
Yes, it's data parallel, but they have very different synchronization, very different inter-thread communication requirements.
Right. Well, the interesting thing about these 13 dwarfs is that if you look at them as class of algorithms, forget the specific implementation, whether it's auto-tuned or not, they're not surprisingly different from what scientific computing has been about since, at least when I picked up the scientific computing book. So there's a lot of experience there, so it shouldn't be too difficult to tell whether they map to this model or any other model. So without saying that these 13 programs are not important, maybe Dave is right. These are the only things that you need to worry about. If he is right, it's a good thing because we have lots of experience on these programs. And excluding FSMs, which I think it's a relatively sequential program, unless I've missed some development recently, it should be relatively easy to know how we can eliminate communication, block them nicely, do them functionally, whatever. These are all programs for the most part, all programs.
Any other questions?
Fundamentally, we disagree with anything that comes with support. Our visual opinions of this one.
Again, the paper, there's a link to the paper section there where you can download the paper. So,
Thank you.
great, thanks.